All right, so this is a test presentation of what's gonna be the presentation that I'm gonna have at our science reading club at Preply, which we have together with the rest of scientists and also many engineers that participate into this. It's an interesting moment to discuss about the latest hot topics in research, but not only about papers, scientific publication, but also it might be about a repository or blog posts that we might read throughout our days. And it is about a moment of not only for not only presenting a specific topic, but also to discuss about how can we draw lessons from uh, others people research, other companies research, and how we can potentially apply it also in our own work, in our daily work, in our models, whether it's about recommendation systems or also other use cases which we are targeting in multiple teams. The topic that I've chosen for this presentation, it is about recommendation systems, but specifically how to make them in a way more LM friendly, and how to tackle one of the biggest challenges that we have nowadays with recommendation systems within certain latency constraint. Okay, for regarding this, the presentation will be around a paper that I've read recently. And it is actually a pretty recent paper. So it was published like 3 weeks ago. So it's super recent. And what I'm gonna do is in this presentation, start with the main motivation, the high-level problem setting, and I will later slowly introduce what are the innovations introduced by this HyTRec paper. And there will be also a moment where I will go into the details of the core uh, additions that have been added by these researchers to the Delta network models. And later we will focus on also the architectural part, meaning how they managed to um, put everything together, meaning their innovative parts of the model together with more traditional components of the transformer architecture. At the end, I will dedicate a bit of time, of course, to evaluate what's the result that have been obtained with this novel approach compared to baselines. And there will be, of course, space for questions. So as usual, we dedicate also a lot of time for discussions and answering questions from other scientists in the team. And that is the moment where we're gonna let our ideas go wild and potentially also think about use cases where we could apply some of the ideas expressed in this paper in our own work. All right, let's start with the high level setting of what is the main problem that we're trying to solve with this paper. In modern recommendation systems, we have in many platforms, this specific paper focuses on e-commerce, but this can be applied also in any other scenarios using recommendation systems, most of them, I would say. Nowadays, with recommender systems, where platform have access to super long logs of events for each user. There are cases where we have, for example, access to behaviors, events, where we are in the order of thousands, if not tens of thousands of events per user. And it is important in order to recommend the next item, whatever that could be, what it could be a next purchase or something else. In this case, it's e-commerce. So, okay, the next item recommended to the customer. It is important for this task to be able to look at the entire history of events for certain users. So not the last session. So meaning let's look also at what the user did in the past. because this long history, the whole history of events that we have per user, encodes not only what are more or less the stable preferences of certain users, but also what are the short-term spikes, meaning what are those are moments, periods where the behavior slightly differs from the average. And that could be due to events, for example, Christmas, or it might be Easter, or it might be the Amazon Prime days or similar types of events that are short-lived, meaning it's just a slight deviation, then the user go back to the more or less stable preferences. The objective is to nowadays, with more with the latest recommendation systems, is to move away from collaborative filtering to closer to a transformer-like architecture. Why? Because we want to use the expressive power of such models, which nowadays are pervasive and they are used in all sorts of use cases. What is the main problem? Is to find the balance between this expressive power and also the efficiency required in these use cases, because we often have very strong latency constraint, which we cannot not consider in our work. Meaning we cannot wait forever or for a long period of time to have the predicted output, predicted next item, because the user cannot wait forever in the platform before making a next decision or looking at the recommended items or similars. All right, so in more details, let's look at the complexity side of transformers and why we cannot use them as it is in terms of architecture. As I said before, transformers are very good at capturing the granular changes in behaviors, whatever, or behavior, in this case it's behaviors, but it can be any element in a sequence. The problem is that the way transformers are built with vanilla self-attention requires us to have n by n attention matrices, which cause then the complexity, the computational complexity, to be quadratic in the sequence length n. And that is why you see O of n squared d. D is the dimension of the query key and values matrices, the short side, let's say, of those matrices. And that is usually much smaller than n. So we just consider n as the main factor for the complexity. And this causes big problems, because with ultra-long sequences, this complexity really kicks in and it becomes unfeasible to apply transformers as they are in latest constrained environment. That is why there have been alternatives developed which are more linear. Linear in the sense that the computational complexity is linear in the sequence length, but quadratic in the other dimensionality, which is the dimensionality of the query key and value matrices that we keep. But this is more manageable because D is much smaller than the sequence length n usually. And that means that we still consider these implementations linear in the sequence length. We don't pay too much attention on the quadratic part of this complexity, which is in D. What is the main problem with this approach? Is the fact that we lose a bit of precision, accuracy. Injectivity in this case means simply the fact that we might map different sequences to the same state. So we lose a bit the ability to discriminate different states, different variations, slight variations in the input sequences in order to predict our next item in this case. Okay, So we will be looking later also at the math side of the paper. And for that, we need to have common notations that we all understand, starting from the user set that we have, U, capital U, and together with the item set I. For each user, what we have is um, a sequence of interactions, behaviors, events that is of length n. And the objective that we have is maximizing the probability of the next item, the x of n plus 1, so what is to be predicted as next item for that user. And given the interaction sequence that we have access for that specific user. So this is, I would say, pretty common setting for any recommendation systems. So nothing new on this side. Let's go to the design goals of HyTRec. HyTRec, what it tries to do is maintaining near linear inference complexity for super long sequences, but at the same time, keeping the high fidelity, high precision, the high expressivity of what the vanilla transformer architecture has. So the vanilla transformer with self-attention, softmax self-attention, they want to keep that as well. At the same time, they want to take into consideration also the temporal aspects of all these behaviors, of all events captured in the sequence of interactions per user. Meaning they want to have the possibility to, in some way, tell this is an event from a recent period that might be good to be considered in the next item prediction, because we are in that phase where there is a deviation from the average, or in this case, in this specific case, looking at the average long-term preferences is better. And so this is the temporal part that they are focusing on. In terms of metrics, they evaluate not only accuracy, if we want to call it in this way, which is expressed through hit rate, NDCG, AUC, which we are going to be to look at in more details later on, but also they want to evaluate the efficiency of the model, so the throughput, for example, because that is the other side of the performance of a model that needs to be evaluated, especially in these scenarios. Okay, how do they do this? How do they implement these high-level design goals in practice? First step, for every sequence that we have, for this sequence of n interactions, what they choose is, first of all, a cutting point, meaning they split the sequence into two parts. They define a high-level hyperparameter k that represents what is the number of events that falls into the short-term subset, and all the rest will fall into the long-term history. So the last k events, k is usually small, and it is a hyperparameter that they fix at the beginning. They should represent, in a way, the session-like behavior. So what has happened in the session or in the very recent history. All the rest represent the long-term averaged, in a way, interests of that specific users. Why do they split this? Simply because later on, what they do is they create an architecture that is split into two parts. There are two branches, as you can see at the bottom. There is one branch, which is the one at the bottom, which is the short-term branch. That is simply a standard multi-head self-attention with softmax. Nothing fancy, meaning nothing novel added there. Is just vanilla kind of transformer. And what it does, this branch, is process all the short-term events that we saw before. Those K events per user, K interactions per user, those go through this branch. And that is the most precise one, meaning that is the one that has the quadratic complexity and the highest expressivity. The other branch, the one at the top, that is where the paper focuses more on, meaning it's a hybrid branch made of some normal vanilla softmax attention blocks, and then there are many other blocks which are based on the TADN, Temporal-Aware Delta Network. This is what we're going to focus our next slides on. And in terms of ratio, they use initially 7:1, meaning there is one softmax attention layer and 7 of the TADN ones. They also tried with other ratios, but yeah, most of the evaluations that they do, they did it with this ratio, so 7:1. And that is the part, this branch, that tries to get as close as possible to a linear implementation of attention. And that is the path through which most events go through, meaning all the n minus k events that of the long-term subsequence go through this branch. And then finally, there is a fusion, very simple fusion, where the hidden representation coming from both branches are simply merged, concatenated, go through a linear layer, and then softmax to have the final predicted item across the distribution of possible items that can be predicted. Okay, so at this point, let's go into more low-level details about the implementation of, in particular, the linear attention. As we said before, the softmax attention, the vanilla one, has the problem of being quadratic, of having quadratic computational complexity in the sequence length n. Why? Because from the formula of the softmax attention, we multiply query and the transposed of the key, each of which is n by d, and they output a matrix that is n by n. So what happens is inside here, that is where the problem is. This matrix is super big, especially when the sequence length n is very, very high. What we're trying to do with linear attention is we're trying to keep the operations more or less the same. We still have query key values. We still multiply them in similar ways, but we can't say that we reorder the operations. We just change the operations in order to avoid having at some point big matrices of n by n. So with this reordering, which is in this case, okay, just a conceptual representation equation, which is going to be implemented in a bit more complex way, we're going to see later on. But here, we don't have any n by n matrix. We just end up with at most a d by d matrix. There are many implementations that can make this conceptual equation like a reality. What they do in the HyTRec paper is to go with a recurrent space, a state space recurrent implementation, meaning they keep a recurrent state. They keep throughout the different blocks, the different events. They keep updating it, and then they calculate. They try to approximate the attention operation in this way. We're gonna see the details later, of course. All right. Having said that, if you remember, before I said that one of the design goals of HyTRec was to introduce temporal information in some way, in the linear attention implementation. What they do is they start with this explicit temporal information encoded through an exponential function. So an exponential function of here negative number is an exponential function that decreases. In this specific case, it is bounded between the value is between 0 and 1. And what we have inside the round bracket is the capital T is a hyperparameter. So it's fixed, nothing changes. Is the decay period. So it tells us, it helps us control how fast the model forgets all the behavior from a high level perspective. And besides that, on the numerator, what we have is the difference between the timestamp of the next item, purchase action, and the timestamp of behavior at step T. The higher is this difference, meaning the farther is the step T, the behavior at step T is from the next purchase action, the closest tau becomes to 0. Instead, the closest these events are, meaning next purchase action and the behavior at time step T, the closest they are, the closest tau is to 1. So pretty much simple. Now the thing is that we are going to embed this tau into a bit more complex equation. What we're going to do with this tau is put it into a gate, a temporal-aware gate. So this G of T that you see at the bottom is a gate that later on will allow us to say, should I consider more the long-term preferences? Should I consider more the short-term deviations along that line? So let's look at the step-by-step how we get into all these gate formulation. H of T is a hidden representation, a step T. So imagine is kind of embedded representation of at step T. And H hat here is instead the kind of sequence mean. We can think of the mean of the entire sequence for a specific user. So we can consider as an average long-term preferences for that specific user. Delta of H of T is simply what is the difference between the current hidden representation at time step T and the long-term averaged mean of this hidden representation. This is just the difference. And the second part that we need in order to build the gate formula below is the static gate, what they call static gate. Why they call it static? Because if you see in this softmax formula here, there's no utilization of temporal information. There's no tau, for example. It's just, in a way, we can think of this as what is the correlation? What is, in a way, the correlation, even though it's not mathematically correct, but how they relate to each other. H of T transposed, the hidden representation at time step T, and the long-term preference vector H hat here. And then it's simply a softmax version, a softmax of this result, normalized. What we're going to do is we're going to build this gate, temporal-aware gate, by combining two components. The one on the left is simply the concatenation of the hidden representation H of T with the short-term deviation that we saw before. After we concatenate this, what they do is they pass it through a linear layer. That is why you see the product with the matrix, the weight matrix WG, and the sum with the bias B is simply a linear layer that goes through an activation that is the sigmoid, this symbol here, And all of this is then multiplied by the temporal factor that we mentioned before, tau. So this all first half of the equation of g of t simply is what they call dynamic gate, the dynamic signal. That means the one that takes into consideration the time, the temporal information. Because the second half of the equation is the g static, which doesn't have it. All of these two components are weighted by a parameter that is alpha, which in a way tells us, okay, how should I balance this dynamic versus static gate? All right, so I know it might be a bit now convoluted, but we're gonna get to the end of this, because after this component, we're gonna explain fully the Temporal-Aware Delta Network. The rest is gonna be pretty easy. So what we're gonna do now with this, what we do is we update the hidden representation h of t by using the gate, and using this gate to balance how much of the short deviation delta h of t should I consider for this new hidden representation, how much of this instead should I consider for the hidden representation at time step t, meaning how much should I take from the difference, and how much should I take from the actual representation instead at time step t. Okay, so with this, what happens is if g of t is pretty large, then we're gonna emphasize the short-term deviation, first part. That means we're gonna emphasize the short-term spikes, flash sales, for example. If g of t is small, then we're gonna get the second part kicking in, meaning the model leans on more long-term representation, h of t, the hidden representation at time step t, without considering the difference between that and the average. So this is for stable preferences. Okay, so what we're gonna do finally is we're gonna build, as I mentioned before, the linear attention implementation that they go for is the state space recurrent one, meaning we're gonna keep updated a state space, a recurrent state that is s of t, which depends on the previous one, s of t minus 1, and that is weighted by a factor here, which is in round bracket, which at some point has in between, among all the different operators, g of t. So this is actually not something that they novel in this paper. This is gated delta rule that already existed. What they simply did, it was changing how to properly gate the state, the previous state versus the current one, and in order to be able to consider that temporal information I mentioned before, because the rest, as I said, is not new. It was already there. Now, what we can see here, we can see that S of t in the end accumulates outer products, the product between values and key matrices on the right hand side, weighted by a parameter beta, and it combines it with also the previous state with a decay factor. And the decay factor has, as we said before, g of t, this gate formula, that depends on the tau factor we explained at the beginning. Okay, so now what you can say is, okay, what we're gonna do with this S now. So this one is actually used to compute the output. So if you remember, the attention vanilla one is the softmax of query key multiplied, divided by the square root of the dimension d, and then product with the value. In this case, with linear attention, we take this state S of t, we multiply it, which depends on the value and key matrices, and we multiply it by the key, the queries, to get the output. Then it goes to the next block, and it happens again. The hidden representation that we mentioned before, h tilde of t, that is used to derive the key and the value matrices through linear projections. The dimensionality of S of t is d by d. So as I said before, we are never going to get to a point where we have an n by n matrix. We just have at most d by d ones. Right, so this slide is simply the previous one, but just written in a different way. So why? It's because I want to let you see the state S from a different angle. Meaning that in this case, the previous state, if we unroll this previous state S of t minus 1 multiplied by this decaying factor plus the product of decay, what we get is simply that this decay factor becomes like a decay mask. Meaning that for every time step t, for every time step I, I'm gonna say how much, what is the importance that I should give? What is the relationship that time step I is with j? And this decaying factor is gonna say, okay, through the formula that we said before about the g, this might be important, this might not be important, this is too far back in time, this is instead new, there is a short spike, there is not a short spike. So all of this is embedded in g, which with the product or also to the key and beta is gonna tell us this information. So this, how much one step influences another. And if we just rewrite this product here as d, then we can see that the output is simply the sum of this product between the value and the keys, weighted, decayed by the factor d. All right, so I think at this point we went through the most difficult part. So it was the more convoluted part, just to say all of this to implement a linear attention that is linear in terms of computational complexity in the sequence length n. So the rest is super easy, honestly, because we have the short-term branch, which has only k events. And for this, we just can use the standard transformer encoder with multi-head self-attention. We have multiple heads, same query key values. But here, at some point, we're going to have the n by n matrix. Actually, the k by k matrix. Because is k is the length of the short-term sequence that we are considering in this branch. Cool. So just to recap, what we have is the long-term branch, the one at the top where the novelties have been added in this paper. They are mainly TADN layers, Temporal-Aware Delta Network layers, with the gating mechanism, the recurrent state that we saw before. Just a minority is a standard softmax attention layers. The ratio is 7:1, but they also did some ablation studies with other ratio values. Why they do this interleaving also in the long-term branch is because we can think of the softmax attention layer as the checkpoints, meaning like at some point we want to resharpen the representation, that the granular low-level representation that might have been lost in the TADN blocks. And honestly, I mean, it seems like it worked from the evaluation we're going to see later. So yeah, the ratio doesn't have to be necessarily 7:1, but having this interleaved type of architecture is definitely beneficial. Nice. So as I said before, the fusion part of the two branches is super easy, meaning we take the final representation from the long-term branch and the one from the short-term branch. We just concatenate it, go through the MLPs, and we're gonna get the output straight away, basically. In theory, the long-term branch should encode mostly the stable preferences. The short-term branch instead should capture better, with more higher precision accuracy, the current shopping intent. Let's go into the evaluation part, super important. So we have described what is the approach, what is the result that they come up with. What they used is a public dataset, which is the Amazon dataset that has actually different subsets for different domains, whether it's beauty, electronics, movies, and TV. And this is a good way to evaluate how this model can handle different types of also items, different types of behaviors. In terms of baseline models, these are the ones that they compared their models to. Honestly, I haven't looked into the details of all of them, but what they made sure is that for each baseline, they chose the number of layers, number of blocks in a way that matches exactly, more or less, the number of flops that HyTRec, the architecture, used, so that we can compare apple to apple. It's not like one model has much more operations to be done compared to the HyTRec one. In terms of metrics, they used three main accuracy metrics, one of which is the hit ratio. And for those of you who don't know, the hit ratio responds to the question, how often do we include the correct next item at some point, somewhere in the top 500 recommended items that we have output. And the NDCG instead is a bit more precise. NDCG stands for Normalized Discounted Cumulative Gain. And what is that is it answers the question, not only did we get the correct item at some point in the list, but also did we rank it near the top where the user is actually most likely to see it, or it's at the bottom. And finally, AUC is the area under the ROC curve, which is the probability that a randomly chosen positive item is scored higher than a randomly chosen negative item across different thresholds. So the objective is to get as close as possible to 1, meaning where is the perfect discrimination. An AUC of 0.5 instead is a random ranking, basically. Okay, let's look at the result. The performance results are the following in this table. The HyTRec ones are the one on the last row. The numbers that are bold are the best in that specific column, meaning the best for that specific metric and that specific Amazon subset. The underlined one instead are the second best. From a quick view, you can see that the HyTRec one are either the best or the second best. In two cases, they are not. But one observation then that some of you might come up with is, I mean, fine, HyTRec is one of the best, but it's not beating the baselines all of the time. The results are not super consistent from this perspective. And that would be a fair point, because the selling point of HyTRec is not just these accuracy metrics, being able to beat the baseline across the board. But the selling point is also the efficiency, because it's fine to look at the accuracy matrices, but it's also super important to take into consideration for different sequence length, what is the drop that we will get in terms of tokens per second that are produced for that specific model and that specific sequence length. Here they compare it with just one baseline model, DHS-TU, which is in purple. And the difference is starking because with that baseline model, as soon as we increase the sequence length, for example, from 500 to 2000, the drop is really considerable, meaning it's almost exponential, this drop rate in terms of throughput. Instead, with HyTRec, the drop is much more linear. Yes, we have a drop, but it goes much slower than the baseline. That means that we can push a bit more the sequence length to higher values while still keeping the same kind of accuracy as we saw from the previous metrics. Nice. So another interesting evaluation that they did, it was to understand, okay, we have these Amazon the dataset, different subsets, different metrics. We also evaluated the throughput. But what happens if we have challenging scenarios, two in particular, where, for example, we have users that have just joined the platform and for which we don't have history of past behaviors. Or the other one, we have users that have been with us for a long time. We have some old events recorded, but for a long period of time, we don't have anything. So there is a big gap. What they did in HyTRec is they applied a very simple augmentation approach, which is let's look at users with similar interests and let's fill the gaps with what they basically purchased or they chose as items, whatever use case it was in particular. So it's very simple. So fill in the gaps with items that are from similar users. Even with this simple approach, they prove with the three metrics that we have seen already before, that the results are pretty much close to the ones that we got before without these challenging situations. Meaning, if you can see here, we are in the range of 0.6366 for the hit ratio, 0.3 for the NDCG, 0.86 for the AUC. If I go back here for the beauty subset, we are in the HyTRec 0.66, 0.34, 0.86 for the AUC, NDCG, and a hit ratio respectively. So we're not that far. We're not that far. That means that the HyTRec approach still handles well challenging situations like this by simply applying a super easy augmentation approach. Nice. So the follow-up questions, this is a penultimate slide, then we're gonna be done. We can start our discussions. The question that came up to me while I was going through this paper, they're all mainly related to the hard-coded choices that they made in the design phase. And in particular, for example, is this k hyperparameter, does it have to be always fixed? Does it have to be fixed for every user, every use case, every scenario? Or can it be instead learned, for example, per user, per context? The same is valid for the choice of the function to express the temporal information, tau. Does it have to be an exponential? Or can we learn a parametric family of decaying function that is, for example, per user? And the same is true for the ratio between how many TADN blocks we should have versus softmax 1. Do we have to fix it a priori? 7-1, 3-1, whatever it is? Or can instead be something dynamic that the model can choose by itself? So these are all questions that would make the model more independent from our own hard-coded choices. What are the key takeaways before concluding this presentation? HyTRec explicitly divide the long user histories that we have, for example, in e-commerce platforms into two parts: long-term, short-term components. In terms of architecture, they process these two subsets with two different approaches. From one side, they use vanilla self-attention transformers, blocks. On the other side, instead, they try to re-implement self-attention through a linear approximation. And empirically, they demonstrate that, honestly, both from a metrics perspective, accuracy, precision metrics perspective, they handle pretty well this different subset of the Amazon public dataset. They are comparable with baselines. Most cases, they are even better. And they also maintain at the same time a high level of throughput. So the efficiency is much better than the baseline. And with this, I want to conclude this presentation. Thank you very much. And we can start the discussion. Thank you.